Hello everyone and welcome back to the channel. I dare say it has finally reached winter in Chicago and my apartment has crap insulation, hence you can see me wearing this hat indoors. I'm hoping to finish up this video fairly quickly so that I can watch the Yankees go smack some baseballs, and then I probably will smack a couple of balls myself as well. So let's go ahead and get to this. Today we're going to be talking about Mesa. Alrighty, so as I mentioned, today we are going to be talking about Mesa, which is a paper out of Google in 2014. Now it's worth noting that I've now done 10 straight Google papers, and I'm going to stop glazing them so that I can do other papers right after this video, because this was the last one on the list that I've been meaning to read. Doesn't mean that I'm never going to do another Google paper again. I reserve the right. I'm just not going to do it for a little bit because I'm bored of them. So let's go ahead and get through with this last one. So Mesa, what is it? Basically, it is a data warehouse. It is useful for when you want to perform a ton of analytics, but also it's good at handling low latency queries as well, right? If you do have an OLTP type query where you just want to make a read, Mesa might actually be well suited for something like that. So it's using commodity hardware, which means it's a lot more scalable than using specialized hardware, but we'll talk about that in a little bit. And of course, like all of the other systems that we've read about, they are, of course, trying to be able to be resilient to data center failures. It is strongly consistent because they basically say, well, you know, if our data views are inconsistent, we can have business or legal issues. That's not going to be good. And the way that they achieve this is by actually using these batch updates. So I think this is probably the piece of the paper that I want to focus on the most because to me, having read the other papers in the series, this is the piece of the system that I found to be the most novel and that really differentiates it from everything else. So I guess the question should start off with why Mesa, right? I've mentioned that we have strongly consistent systems elsewhere in Google. Some of them, for example, would be things like Spanner and Megastore. And basically what those guys don't really provide, at least within Google, is extremely high update throughput. Right? Like Spanner and Megastore, they can write fairly fast, but every single write requires a Paxos two-phase commit, and as a result of that, they can't really be that fast. It's just not going to be good enough. And so what Mesa does instead, like I mentioned, is it does this bulk upload process. So you can't necessarily see data instantly, but because we're writing in batches, you can see data relatively close to instantly, and we can get very good update throughput. As far as technology outside of Google or anything that they might have been using up to this point for their data warehouses, basically they might support bulk uploads as well. However, the problem is they mainly support them at infrequent intervals, right? Maybe every hour, maybe every day, and that's really not good enough. Ideally, they want to see these updates within a few minutes. Additionally, many of the data warehouses that do exist, they quote Oracle specifically, use a bunch of expensive custom hardware. So maybe they're really, really parallelizable. However, it's not exactly easy to basically increase or continue to vertically scale when you're using custom hardware because of the fact that you basically just have to be really precise with your hardware needs. This is expensive stuff, and as a result, it is not easy unless you're really, really good at capacity planning. Cool. And then lastly, there are many different views that need to remain consistent with one another. So we've spoken about these in our concept series a little bit. But we've got all sorts of materialized views. We've got all sorts of data cubes that we have to keep consistent. And then, you know, maybe we've got multiple different indexes or multiple different sort orders over the keys that are important as well. And I think it's worth noting that, you know, because of the fact that we're trying to be resilient to data center failures, we're going to be running multiple Mesa instances across these data centers, and those have to be strongly consistent as well. Okay, so how does Mesa store its actual data on disk? Well, this should hopefully be fairly familiar at this point because there are quite a few other papers that we've talked about that are doing something pretty similar. Basically, Mesa is going to be using column-oriented storage. The reason that they do that is because it allows us to compress data, which allows us to minimize storage costs. But in addition to the compression, which keeps things nice and cheap, it also means that basically we can only select a subset of rows, which is good when there are tons of rows in a table, which is very possible for a massive data warehouse like this. Because of the fact that we care about our read speeds a lot more than our write speeds, we always want to choose a compression algorithm that's going to emphasize this decompression speed. That's just going to be crucial because we're going to be decompressing data a lot more than we're going to be compressing it. We just compress it when we write it. And then again, because of the fact that we're doing column-oriented storage, regardless of the fact that those column values are stored together, they're going to be sorted by the actual key that they belong to itself. So basically, you know, all this data is indexed by some sort of key. And so think of these just as a bunch of immutable files, right? Where each batch upgrade or each batch update every single time that you do one ultimately gets converted into a bunch of immutable files. And then each one of those files is sorted by the key that it's indexed by. And then now you've got all of these different batch writes. And so you can think of one of these as just the column values for a given batch write. Now it's worth noting that similar to an SS table, we'll also maintain a small sparse index, which basically gives us a little bit of insight into certain keys and where they might be located in the file. And so that way we can quickly look at the sparse index and binary search between the two things that are relevant to us to find a key that we are particularly interested in. Next, let's go ahead and talk about batch data uploads. So this is really the bread and butter of the system here, and so I'm going to try and spend a little bit more time on it. This slide is visual, but hopefully we all understand what's going on by the end of it. So I guess the first piece of the puzzle here is this system called Colossus. So Colossus, think of it as just Google's next generation GFS. It's effectively, think of it as GFS. So because of the fact that all these files in Colossus are fault tolerant, it basically means that they are already from the start in multiple different data centers. So I've basically laid this diagram out by multiple different data centers, and so hopefully that will give you a better picture of how this thing remains fault tolerant across different geographic areas. So we have a bunch of random processes that we're just running on a loop. They're completely stateless, but they are called the committer. So the committer is going to basically every couple of minutes look at these Colossus files. And keep in mind that for something like a file system, any application can go append to those files. And so at some point, the committer is going to say, you know what, I'm ready to create a new batch. This is exactly going to be the new batch, and any other file that's created after this, I'm just going to disregard that for now. That'll be in a subsequent batch. So the committer then says, okay, so here's our batch. Let's say it's this particular committer, because this guy can be redundant as well across data centers. So this guy over here says, hey, we're actually going to create a new batch with version number 25. And the files that that's pointing to are this guy right here. So where it's going to write that to is this versions database. So the versions database is really the one piece of this puzzle that has to be strongly consistent, right? Because the versions database is saying for every single Mesa instance, which batch updates have I applied and which batch updates have I not. And so, of course, if it needs to be strongly consistent, that means we want to be running Paxos. And of course, if we want to be resilient to data center failures, that means we need to run it across data centers. So as you can see, we've got a Paxos replica in every single one of the data centers. So like I mentioned, the committer is basically going to determine there's some sort of new batch. We've got a bunch of files here that are going to determine the data included in that batch. And then all of that is going to be written to the versions database, which again is fault tolerant as a result of it being Paxos. Cool. So now what's Mesa doing? Mesa is going to basically be periodically polling from the versions database. And then we've got some sort of job scheduler that's doing that polling in every single data center. And then from there, it can enqueue a bunch of tasks onto all of these individual little worker nodes. Now the worker nodes are going to read the data from Colossus. They're going to perform any of the necessary compute that needs to be done to basically make this a valid Mesa batch. So maybe they're creating materialized views, maybe they're sorting the data in a certain way, but obviously there's a ton of processing to be done, and so that's why we have many different workers to do it. We have a bunch of worker pools. And then once that's done, basically the committer is going to keep reading from all of these Mesa schedulers and try to determine when that process is completely finished. So note that as the scheduler or as all of these workers continue to finish their own little tasks, they report back up to the scheduler, and then the scheduler stores all of its state in Bigtable. The reason we store state in Bigtable is Bigtable, again, is also replicated across data center, and it means that if the scheduler goes down, we can bring up another scheduler, it reads from Bigtable to see the current state of the world, and then it can start directing all of these workers again. So the point is here, our committer now is listening for all of the Mesa instances, so all of these instances across data center, to see if they've done all the processing that they needed to do to locally apply this new batch of files. And once they have, then it goes over to the versions database and says, hey, I'm going to commit this now. The versions database is now going to write this to the other Paxos replicas so that that data is fault tolerant. And now Mesa can go ahead and see, oh, wait a second, I've actually can go ahead and show these writes and incorporate them into my workflow. This new batch is now committed, meaning every single query from here on out should incorporate it, assuming that it's asking for the proper version number, right? Because all these batches have version numbers, so that basically means we can use snapshot isolation here. Every incoming query can look at the versions database, figure out, basically I'm going to read from version 25 now, and then the Mesa instances will be able to answer those queries. So we've basically gone ahead and achieved strong consistency. The data itself is processed by each Mesa instance asynchronously. However, we basically synchronously apply it at the same time across all Mesa instances. Cool. Let's go ahead and continue to talk about those batch uploads just so we can formalize a couple more things about them. Basically, every single time that we do a batch update, we call that a delta. Each delta has a version number. Like I mentioned, the version number in this example over here was number 25. The version is only made visible for querying once we've committed it in the versions database, because obviously no one is going to even know that version 25 exists to be queried until it is in the versions database, and then all of the Mesa instances are already capable of serving it. Hence, we have strong consistency. Cool. And then additionally, a nice thing about this is all of our updates are completely immutable, right? We're appending all of these files into Colossus. We put them into this completely write-only database, or like write-only files where once you've written them once, they can't be changed. And so as a result, we don't need any sort of locking, which is really nice for keeping up our throughput as well and avoiding things like write conflicts. And then, of course, as a result of having all these immutable files, what it means is that we can basically read from a consistent snapshot of the database, meaning we're going to have consistent data even across things like different partitions or something like that. And then all we have to do in order to get this consistent snapshot is pass in a version number and say, hey, I want to read the database at version 25, and here's my query that I would like to read. Cool. Now, a nice thing or something that you might note is that obviously as this system scales, the input per batch is going to get bigger and bigger over time. And so it's going to take Mesa longer and longer to process them. And how are we able to keep up with the amount of data that's actually needing to be ingested? Well, note that all of these workers are pretty much completely scalable, right? If we add more workers, our Mesa scheduler can schedule tasks for them all to perform, and then we should be able to keep up with that load. So the next piece of this that I want to talk about is delta compaction. So if you recall, like I said before, the delta just is basically the formalized term for one single update batch and all the immutable files associated with those. You can think of them like all the SS tables for one given update. Cool. And so if we want to read all of the data within Mesa, we basically have to read all of the deltas, right? And that is expensive because now you're reading a bunch of different files, you're combining the results together, and you're ultimately returning that to the user. It would be a lot better if there were some way to basically do a bunch of pre-aggregation of that data. So let's say, for example, that Mesa knows it's creating a materialized view where the view is showing the sum of some field. Rather than having to read all the deltas and sum up the fields at query time, it would be a lot better if we could just combine all of those deltas, pre-compute the sum and cache that on disk, and then just return that. So that's kind of the idea behind delta compaction. It also just helps us save a lot of space in general. So the idea is we can combine these files according to an aggregation function that we know our view is going to be using. And so basically the idea is we'll run the aggregation function on each key from the oldest to the newest version. The reason it's important to use the oldest to newest version when running the aggregation function is that the aggregation function is not always commutative. So for example, let's say we used an aggregation function where it's like f of old value, new value is equal to new value. This is basically an aggregation function that just describes overwriting the value of a key. But if we did that in the reverse order, where it was f of old value, new value is equal to old value, and we basically applied it from the newest version to the oldest version, then we're basically going backwards in time. We don't want that. So yeah, basically what ends up happening is that because of this delta compaction, we end up with multiple different delta files, and some of them can actually reflect a kind of cumulative aggregation of multiple deltas. So you see we've got this massive delta over here that's called the base delta because it reflects everything from version 0 all the way up to some larger version. And then we've got these intermediate deltas. This one, as you can see, incorporates 100 of them. And then we even have multiple tiers as well. This one incorporates just 10 deltas. And then we have all these singletons over here as well. And so this allows us to basically perform a bunch of compaction in the background to speed up our reads and also save a bunch of space. The next piece that I want to touch upon here is going to be the actual query servers. So we've described the writing process in Mesa so far, but how do our queries actually get done? Well, basically we have a pool of query servers, and all that these guys are going to do is go to Colossus, read the appropriate Mesa files that we've stored, and return results. So I guess the idea is, because of the fact that these are separate servers from Colossus itself, we can actually pull from anywhere in Colossus and read results for any table. That being said, that's going to be slow, right? Because now we have to load a bunch of data over the network. And so what's more ideal is some of these servers can actually do a bunch of prefetching and caching of data. So as long as we're able to cache some tables on each server, if we can register for each query server which tables they have cached, we can intelligently route queries to the proper query server that's caching those tables to speed up performance quite a bit. And so another piece of this, besides the whole smart caching optimization, is that Mesa is also aware of certain properties of each query, right? So it knows where the queries are coming from. So let's say, for example, that some sort of user front end is making a query. Mesa might label that one as latency sensitive and then give it higher priority when actually scheduling it to be run, so that ideally you can get a little bit of a lower latency. There are certain queries that it might label throughput sensitive, right, like massive batch jobs or something, where it doesn't matter if it takes an extra 2 seconds to start running, it just needs to be fast after that. And then those can be a little bit longer to schedule. Cool, so now we're going to talk about a couple of read optimizations that Mesa includes, which I think are pretty interesting. So number one is going to be delta pruning. This reminds me of something that I learned about when I was reading about Parquet. And basically the idea is, if you have an immutable file representing a delta and you know the range of keys in that, which you can basically store when you actually write the file, if you see that a query is fetching a bunch of keys that are not included in that delta, you can just skip the delta in general and save yourself some read time. Number two is this concept of scan to seek. So I have an example here because it'll probably make it a lot easier to understand. Let's say B can have values 1 to 1,000, and as you can see from the table below, A can only have values 1 to 3. Let's say that we're actually writing a query where we care about all the rows where B is equal to 97. Because of the fact that our index is a compound index on A first and then B, so we're sorted on B values within the A values, this would basically imply that we should be doing a linear scan over the table, and now we're fetching tons of rows. What would be a nice optimization is if instead we're able to basically do the following right here, where we translate this query into 3 separate unions. So you can see we're basically doing select star where A equals 1 and B equals 97, select star where A equals 2 and B equals 97, select star where A equals 3 and B 97. Because these are 3 different index reads. So now rather than doing basically a linear scan, we now get 3 times O of log n time complexity, which is going to be much better. So note that this isn't going to improve all query results, but if we have a situation where the cardinality of the columns before the one that we care about is small, so in this case, if the number of possible A values is small, then this is a nice optimization for us. Another thing that we actually go ahead and do in Mesa is we parallelize our delta reads. So what that really means in practice is, if we know we have to read a ton of different files and we have to go ahead and aggregate that data over the keys, well, basically we want to be sure that we are doing so in a way that, if let's say we're using MapReduce, which they do in Mesa, we want to make sure that all of the partitions for mappers are similarly sized. So the way that they actually do this is basically, as we're creating deltas or as we're compacting them and creating a new file representing a delta, we'll actually subsample all of the rows, and every few rows we'll take a tick of what the current row key is. And so that way, for every single delta file, we'll have this subsampling histogram of keys. So you might see, oh, key for Jordan, there's 10 of those in my subsample. Maybe for Corinna Kopf, there's 3 of them, and then for Donald Trump, there's 2 of them. And so maybe if our partition size is 5, that means perhaps I need 2 partitions devoted to the Jordan and then 1 partition devoted to Corinna and Donald. And so we can be a little bit smarter about how that gets done. So I guess the gist here is that, the majority of queries are actually going to be done over multiple Delta files, not just one. And so when we're doing a query, we basically look at all of this, like sample histogram for every single Delta. We sum them up, and then we actually can smartly create our partition boundaries over the key space in order to parallelize efficiently. Okay, another thing to talk about is schema changes. So one thing that I found interesting about this paper in Mesa is that they mentioned that existing data warehouse solutions are really, really bad at executing schema changes, and that a lot of them come with downtime when you're trying to do so, because it was kind of anticipated that the schema doesn't change very often. However, they found in practice, the developers of Mesa, that schemas change all the time, and users are very eager to do so. And so if that's the case, you really don't want to block any reads or writes when we're actually changing our data schema. And so they come up with basically a couple of ways of doing this so that we aren't blocking any existing operations. So one of them they deem as the naive solution, but you can always do it regardless of the type of schema change that we're talking about. And the other one is a bit more optimized. So the naive solution is going to double storage temporarily because we're literally just copying all the existing data. We are changing the schema in the background. We're applying any updates that happened while we were doing the copying. And then once that's completely done, we can go to the version database, which contains all the metadata for these instances, and say, hey, our new schema has been applied. Let's start using that instead. Hopefully that makes sense, but again, the downside is we're using a ton of compute, a ton of bandwidth over the network, and ultimately a ton of extra storage. Number 2 is going to be our better solution, or at least the preferred one. You can't always do it because it works for some types of schema changes, but not others. So the reason why is, let's say we change our schema, we're adding a column. And let's say the column is 2 times, basically the way it's computed is the value of that column is 2 times the value of some other column. Basically, as we're doing queries for existing data that's been written without this new column filled out, we can basically populate a default value for it, or do the computation of the 2 times x at query time on the fly. So it adds a little bit of extra compute, but ultimately it's fairly negligible. And then when we eventually do compact these files, right, because this is old data, it's going to get compacted with new data, that's when we can go ahead and write the default values to disk itself. So note that this works for something like adding columns, but if we're talking about, saying, reordering keys due to some new index value, this is not really something that we can do on the fly. It's just not going to work out. We're going to have to use our naive solution. Okay, the last piece to talk about here before we go into our conclusion is going to be data corruption detection. So we spent a lot of time talking about this for GFS and just how data can be corrupted on disk. Because we're using commodity hardware, things can get faulty. Bits can get flipped, and then you want something like a checksum to basically compare against your data to ensure that nothing has changed. And so a checksum is good for detecting disk failures. However, in a data warehouse like Mesa, they also need to ensure that you aren't having any CPU or memory related failures, right? As I query data and as we're doing computations, due to things like aggregation functions, it's possible that somehow our CPU or our RAM is faulty and bits continue to get flipped and we get incorrect data. That's not going to work for them because that causes all sorts of downstream issues. So, there are a few examples of where CPU and RAM can cause issues. One is during query time, like I mentioned. Another is just like doing delta compactions, right? Because you're using CPU to do computations and run the aggregation function on the deltas. And then also just if we're caching data in memory, maybe on the query servers or we prefetch it or something, it could get corrupted in memory there. And so basically what we can do is take advantage of the fact that we have a lot of redundant data, right? So there are 2 cases where I would say this applies. Number 1 is the delta compaction case, right? Where we're taking, let's say, 2 files and we are combining them into one, equals this guy over here. Because of the fact that we just did this compaction, we have both of these files around locally, we can actually compare these 2, right? We can run some aggregations over them to determine if the data is actually the same after the compaction, or we can also look at the key range cumulatively between this file and make sure that it's the same as the cumulative key range from this guy. And that's just going to be a good sanity check. We can't really use things like checksums between them because they're fundamentally different files on disk. but we can actually look at the data itself and sanity check there. And the same idea is actually going to be the case across data centers, right? Because given that we have multiple instances of Mesa, which should ideally be storing very similar data, the one interesting thing to note is that across data centers, we might have different variants of the deltas, right? So maybe one data center has been a little bit more compacted than another, and because of the fact that these guys actually have different files that are effectively storing the same data, we can again do things like the key range scan, as well as certain aggregations to make sure the data is consistent between them. And if it's not, then you can actually load the data from a good data center into one that has been corrupted in order to restore it. Cool. And so like I mentioned, because these tables may have different delta breakdowns across Mesa instances in different data centers, we can do more checks there and backfill as needed. Okay, so let's talk about a few quick conclusions before I call it a night here. Basically, number one that I think hopefully fairly obvious, but sometimes it does need to be said, is don't over-engineer things. The writers of the paper were very adamant that even though they know they can probably get better performance if they weren't to use existing Google functionality, reinventing every single thing from square one is going to be an absolute disaster and would probably never get done. So take advantage of existing components where possible, optimize them as needed, but don't try and over-engineer anything. Number two is be careful regarding the assumptions of how users in your system are going to act. Basically, in this case, they were like, well, we don't really think very many people are going to be making schema changes in our existing data warehouse, so we're not going to optimize those. We're not going to make it so that they're efficient and non-blocking. Well, it turns out a ton of people make schema changes, so now they needed to go ahead and do this. So definitely think through all the possible ways that users can use your service and survey them rather than just making assumptions about it. Number three is that it is really important to be able to use commodity hardware. Sometimes it's the case that you can't avoid it. For example, it's not like we're using commodity hardware to do neural network training right now. But when you can use it, it basically means that you don't have to buy specialized hardware. Because Google has tons of extra data centers, they can basically add computers as they please to something like Mesa, and it just makes life easier to deal with in terms of scaling up. At the same time, it also introduces all sorts of failures because of the massive scale that Mesa is running at, and as a result, you have to do things like try and detect corrupted data, deal with broken disks, bad CPUs, bad RAM, and you really have to think about all these corner cases. Anyways, guys, I hope you enjoyed this video. I think the nice thing about being done with these Google papers is that I can get into a little bit more popular systems, which may get the view counts up ever so slightly, but we'll have to see. Anyways, hope you all have a great night, and I will see you in the next one.